Hello, welcome to the next set of algebra notes. We're on outcome 6 now. In this section, we're going to talk about solving linear inequalities and compound inequalities. So basically, equations with like greater than or less than instead of the equal sign. So not quite equations, that's why we call it inequalities. Before we can really get into solving those, we want to make sure that we're clear on some the ways we write the answers. Because when you're working with inequalities, your answer is not just going to be one number. It could be a whole set of numbers. There's lots of different ways to write sets of numbers, so we're going to go over a few of them so that you can kind of have these in your head so you know how to do these problems later, how to answer the problems. Also, a lot of these will come up throughout the semester as you're doing your homework. You'll see these notations used, so it's really good just to kind of go over them now so you're ready for them. First one is what we call roster method. It's probably the simplest way to write a set of numbers. Literally, you just list out everything in the set. So for the first example, we want to list the whole numbers between 2 and 7. So we're just looking for whole numbers, no fractions, no decimals, and we just want numbers between 2 and 7. Because it says strictly between, it doesn't say anything about including 2 and 7, we're not going to include 2 and 7 themselves. You know, if it said between 2 and 7 including those numbers, or inclusive or something like that, then we would use 2 and 7, but this is just referring to numbers between. So this is going to be numbers like 3, 4, 5, 6, and that's it, right? Those are the only whole numbers that are between 2 and 7. So roster method, you list them out, and then the way we let everybody know this is a set of numbers, this is one thing, is we put it in what I call curly brackets or squiggly brackets. So we put it inside these curly or squiggly brackets. This is a set of objects. When you're using roster method like this, the order does not matter. So you don't have to put it in order like I did here. I just listed them in order because that was the easiest way to think about what the numbers were. But if you put 6, 3, 4, 5, whatever, it's fine. Also with roster method like this, we typically do not repeat. So if you see a number, come into a situation more than once, you usually don't repeat it. Roster method, we just want to know what numbers there are. We're not really looking for how many times they're in their set. Yeah, that's roster method. So roster method, good for small sets of numbers, and you just list all the numbers. We'll do one more. Here we're using the word integers. Remember, the integers just means both positive and negative numbers. So instead of just the whole numbers, which is positive numbers, integers also include negative numbers like -3, -5, -7. Those would be integers. So this one wants between 6 and 5, but this time it says inclusive. So we actually do want to include both -6 and 5. So the list here, we're going to include -6, -5 is in that set, -4, -3, -2, -1. Those are all numbers between -6 and 5. Zeros in there, 1, 2, 3, 4, and 5. And again, because it says inclusive, we're including those two, starting and ending numbers. And to make it a set, we use the curly brackets, and that just makes it a set of numbers. So this is the list of numbers between -6 and 5, including both -6 and 5. And again, order doesn't matter. If you rearrange that, that's fine. It doesn't have to be in that order. A lot of times we just leave it in order because that's a easy way to write it down, make sure you don't miss something. But you don't need to put it in order. If you put it out of order in my math lab when you're doing the homework stuff, it'll be fine. Now this is really good until you get situations where you have to list lots of numbers. And if I say lots, I mean like infinitely many. We don't want to list all the numbers there are. That's going to be really annoying, and more than annoying, it's going to be pretty much impossible, right? So we don't really use roster method unless we have small sets of numbers, really small lists. If we have infinite lists, so then we have to use something else, and that's why the first method we're going to use besides this is called interval notation. This is developed for a situation where we have infinitely many numbers. You don't want to just include a couple of numbers. So in this situation, we're going to start off with numbers greater than or equal to -7. And we want to write that in interval notation. Now, interval notation always works the same way. You always start with the smallest number possible and then write the biggest number possible. So in this case, since we want numbers greater than, bigger than, or equal to -7, the smallest possible value is itself -7. Because you can include -7. That's part of the set. Equal to -7 means -7 counts. And then I'm going to go as big as I can. Well, since I don't want anything bigger than -7, I can just keep going forever and ever and ever, right? -8, -1,000,000, -2 billion. Those are, or sorry, positive 8, positive billion, positive 2 billion. Those are all bigger than -7. Those numbers all work. You can go as big as you want. So we're going to use the infinity symbol, right? Because there's no limit. You can go as large as you want. So anytime you have no limit, it just keeps on going forever and ever, we'll use the infinity symbol. Now, with this interval notation, you have to have a way of indicating whether or not the number is included, because I'm going to include the -7, but I can't include infinity, right? Infinity can't be included because you can't actually reach infinity. I know in grade school you always make that joke about like infinity times 2 or infinity plus 5, saying it's bigger. It doesn't really work that way because infinity is not a number. You can't just add 5 to it. Infinity is the idea that you just never stop. It just keeps going and going and going. So when you have something like this, you can't reach infinity. So to show that, we use a special symbol. We use the curved parentheses or curved bracket. So this parentheses or curved bracket means that you get close, but we never quite reach. So we get close, but we don't reach. Because we can get as close as we want to infinity, right? We're going to go on forever and ever and ever. It never stops, but we're not going to reach infinity because you can never get there. But we don't reach. So we don't actually make it all the way to infinity because you can't ever get there because infinity keeps going forever. Now, if you want to include a number, because we want to include -7. -7 is part of this set. We don't want to get close to -7. We want it to include it. Then we use a hard bracket or a square bracket. So hard bracket or square bracket means that we do include that value. So we actually reach it. We reach all the way up to -7, and we hard stop at -7. I always think of like the square bracket. It looks like a hard stop. Reach the wall. The parentheses here, you can kind of see it's a curve. You get kind of close to it, but you never quite reach it. That's your parentheses. But the bracket, we do include this value because we actually reach it. And so that's interval notation. Honestly, interval notation is probably the most important one we're going to use today because it's the one you'll answer a lot of questions in. We've already seen a little bit of interval notation. We're talking about domain and range, so this shouldn't be a complete surprise to you. But yeah, interval notation, it's going to come up all semester long. We'll be using it all semester because we'll be talking about domain and range. That's one reason we use it. And it'll just pop up other situations too where we have a set of numbers that we want to include. So this is going to be important, this interval notation. Let's do one more with this. Here I have the numbers between 4 and 17, and we're going to include 4. So we're not including 17, but we are including 4. And we want the numbers between 4 and 17. So this one I would list it out. I'd start with 4. Because I'm including 4, I can start with 4. I know that's a bracket because I'm including 4. And then I go to 17 and I think, okay, where do I stop? Well, do I stop at 16? Well, no, that doesn't work. If you stop at 16, then you would miss 16.5 because that's between 4 and 17. If you try and stop at 16.5, well, you miss 16.9 because that's still less than 17. If you try and stop at 16.9, well, that's not good enough because 16.999999999, that's also between 4 and 17. So because we can't pick a number to stop at that's less than 17, it doesn't work that way because there's always one more number further up that's closer to 17 but still not there. What we do is we actually put a 17 here. So we're going to get close to 17, we're not going to reach it, and that's why we like this parentheses, because then we can put the parentheses say, we're going to go from 4 to 17, but we're not going to ever quite reach 17. You can get really, really close to 17. So like I said, you can get that 16.99999, but you can't reach 17 because 17 is not included in this set. It's only including 4 and the numbers between 4 and 17. So again, the parentheses means we get close, but the bracket means we actually reach the value. So it's the list of numbers between 4 and 17, including the 4. That's interval notation. Now there's one more notation I want to talk about here. It's not something you will use a lot. Like we're not going to answer a lot of questions with interval notation, with this next notation, but it is something you'll see the book use in math lab, your homework. This is something people use all the time. It's called set builder notation. So set builder is just another way to write a set of numbers. But instead of just listing the smallest and the biggest and then calling that your set builder actually makes a rule and then talks about how all the numbers have to follow that rule. So like this interval right here, looking at this interval, we can see this is the numbers bigger than 3.5, right? Because we got the 3.5 is the smallest number. Infinity is, as far as going forever. So this is just anything bigger than 3.5. There's no bracket here, so we're not including 3.5. So the rule for this set of numbers is the numbers have to be bigger than 3.5. So what we'll do is write an inequality where we use x to stand for our numbers. You can use other variables. So you might see set builder with a y or z or something else. I'm just using x because that's kind of the typical variable. But we'll use a letter like x, and we'll describe it by making a rule. We'll say, okay, the numbers have to be bigger than 3.5. We'll say x has to be bigger than 3.5. That's using that greater than notation. So this is that my numbers, because x is going to stand for my numbers, the variable, so it can be all the different values that work. The numbers have to be bigger than 3.5. Okay, now to make this a set, this isn't enough to make a set. This is just describing the rule. To make this a set, we're going to put a little frame around it. And the frame looks like this. You put a bar here. We put the same letter. So if you use x, you have to use the same letter x. If you used y, you use the same letter y. And then we'll put a squiggly bracket around the whole thing. Now we already know squiggly brackets are a way to list sets of numbers, right? Because we use that for roster method. So the squiggly brackets, or curly brackets, curly brace, whatever you call them, those guys say this is a set of numbers. So this is a set of numbers. And then the x here says these are our numbers. Our numbers are these values x. So x stands for all our numbers. And then this bar is actually a way to say such that, or it follows this coming rule. So the numbers, x stands for numbers, follow this rule. And if numbers follow the rule that the numbers are bigger than 3.5, then they fit into this set, right? So this means that the numbers follow the rule that the numbers are bigger than 3.5. That's set builder notation. So instead of writing out the smallest and biggest, instead of writing out the list of answers, we make a rule and then say the numbers have to follow that rule. So you see how the rule has to have an x inside of it, in this situation, because x is representing my numbers, and so my numbers x have to follow this rule that the numbers are bigger than 3.5. That's set builder notation. Again, I'm not going to make you answer stuff in set builder. Not really worried about you using this, practically, but I am worried about you being able to recognize this notation and know what it means, because you'll see this in my math lab. You'll see problems where they'll use the set builder notation. They'll have a variable, the bar, and then some kind of description. It doesn't have to be something like this where it's greater than or less than. It could be any kind of rule. Like you could make one, just a little aside, let's make one aside. You could have one where you say the set is my numbers such that my numbers are even. And that's the set of numbers, right? This is all the numbers that are even. That's a set of numbers. So 2, 4, 6, 8, those are all even. They would fit in this set. So you don't have to use a greater than or less than. You could use any kind of rule. You just have to make a rule about x. So here, the x's are even. The x's are even. So then this is the set of even numbers. That's just a way to do it. So just, that's kind of how set builder notation works. You come up with a label such that it means that it follows the rule, and then the rule that it follows. Okay, let's do one more set builder notation. So here we go. I have the interval from -infinity to 5. So you can see this is going to be all the numbers smaller than 5 now, because I'm going 5 and less, but it also includes 5. So if I want to do this one, I'm still going to do my squiggly, my x, my bar. I'll close it off at the end with a squiggly, but now my rule is going to say that my numbers have to be less than 5. So my values x have to be less than 5, but also I need to include 5, right? Because there's the bracket there. Remember, that means that 5 is included. So I'm also going to put an equals to, because remember this is less than or equals to. It means that it could be either less than 5 or it could be equal to 5. Either way works. So 5 works because it's equal to 5. Numbers like 1, 2, 3, 4, they're less than 5, they work. So this would include all those numbers. This is the same way, same set as that, just 2 different ways to write it. So again, there's interval notation and set builder notation. On the test and stuff, I'm going to be asking for questions answered in interval notation. So you'll see that come up on the test. That's the important one that you'll definitely want to be able to write numbers in this notation. Again, it's the smallest number then the biggest number, brackets for including the number, parentheses when you don't include it, when it's not part of your set. Okay, so now we know how to write the answers to these questions. Let's talk about the rules for solving inequalities. Now, thankfully, inequalities, when you work with inequalities, they work a lot like regular equations. You can add to both sides. You can subtract from both sides. You can multiply and divide both sides. And typically, it works just the way you'd expect it to, just like equations. So I'm going to show you a couple examples. First off, the addition principle. This works for both addition or subtraction because, of course, you can think of subtracting numbers as just adding a negative. And it works the same way. If I subtract 5, or if I add a dead of 5 or a negative 5, either way, it's going to go down 5. So I could take an inequality, and I can add something to both sides. So say I take the inequality and add 3 to both sides. So I add 3 to both sides. 2 plus 3 is 5. 5 plus 3 is 8. And just like 2 is less than 5, 5 is less than 8. So adding the same amount to both sides, it will never mess up the inequality. The inequality will hold. It will stay true. So you can do that. You can always add to both sides. This is just an example, but this rule applies. You can always add to both sides. You can also subtract from both sides. So if you want to, you can take and you can subtract the same thing from both sides. It still works. If I take 2 is less than 5, and let's say I want to subtract 7. I'm going to subtract 7 from both sides. We'll do a big subtraction. 2 minus 7 is negative 5. 5 minus 7 is negative 2. And negative 5 is less than negative 2 because it's more in the whole, right? I know it feels weird to think 5 less than 2, but we're thinking negative 5. So this is more depth. So it's worse off, right? This is smaller than negative 2. This is still true. The inequality holds. Whether you're adding or subtracting, either way the inequality holds. So you can always add or subtract to both sides, just like we do with equations, and it works just as well. Multiplication, you got to be careful because there's a separate rule for positive multiplication and negative multiplication. So if you're multiplying, and we're going to treat division as part of this because you can always think of division as multiplying by a fraction, like a half or a third. So for both multiplication, where you multiply both sides, or division, divide both sides by a positive. And that's what they put the c is greater than 0 here. This is just saying that the number you're multiplying or dividing by, the c, is positive, bigger than 0. So if you multiply by something bigger than 0, then it's going to work. Your inequality will stay the same. So for example, here I'm going to multiply both sides here times 2. Negative 3 times 2, 4 times 2. 2 times 3 is 6, and a negative times a positive is a negative. 4 times 2 is 8. And guess what? Negative 6 is still less than 8. Big surprise, right? But we said that that's the rule. If you multiply both sides by a positive, you multiply by a positive on both sides, it's going to hold. The inequality will stay the same. If you divide by a positive, this works as well. So if I take negative 3, less than 4, and if I divide both sides, let's divide it by 4. I can divide by whatever I want as long as it's a positive number I divide by. It works. Well, 3/4, that doesn't come out nicely. It doesn't divide, so we're going to leave it as a fraction. We'll leave that as a fraction of 3/4. But 4/4, you're going to divide that, you get 1. And yeah, negative 3/4 is still smaller than, less than 1. Remember, if you're having trouble with your inequalities, remember that the small side is the small number, is the point. The big side, this open side, that's the big number. I always think about alligators and how alligators are looking for a big meal they want to eat. So the alligator eats the bigger number over here. So that's what the opening is opening towards. It's opening towards the bigger value, right? I know it's silly, but it works, right? You think about the alligator opening towards the bigger number. 1 is bigger than a negative, right? Because this is a positive, that's a negative. And so the inequality holds. The inequality holds. It stayed the same because multiplying by positive does not change it. Now, where the thing that does change it is when you multiply by a negative. And the same thing for division, right? So multiplication or division by a negative, something less than 0, which makes it negative, that actually flips the inequality. So you see they start with a less than, they end up with a greater than, and vice versa. It works the other way around. If you start with a greater than, you'll end up with a less than. So the less than turns into a greater than when you multiply or divide by a negative. So for example, if I take both sides here, 6 and 8, and I divide them both by negative 2. So we divide both these by negative 2. Well, 6 divided by 2 is 3, and a positive divided by negative is a negative. 8 divided by 2 is 4, and a positive divided by negative is a negative. And you can see that negative 4 is actually smaller, right? Because the inequality here flips. Negative 4 is further in the whole, so it's less than the negative 3. So it flipped. We started with a less than, it turns into a greater than symbol, saying the 3 is actually bigger now versus with a 6 that was originally bigger. So we flip the inequality if we multiply or divide by a negative. That's an important rule. That's kind of the really big distinction between working with equations and with inequalities. With equations, you don't have to worry about flipping it because an equal sign works the same way either direction. But with inequalities, when you multiply or divide by a negative, you have to flip the inequality. You flip it around so it points the other direction. Let's show the last one here. Just show this. If I take 6 and 8 and say I multiply by a negative, so instead of dividing by negative 2, let's multiply. I'm going to multiply by negative 3. Just for negative 3, that's what I'll multiply for. So 6 times 3 is 18, and a positive times a negative is a negative. 8 times 3 is 24. Positive times negative is a negative. You can see that negative 18 is less. Oh, wait, no. It flipped, right? It's more than negative 24. So it's flipped. So now actually the negative 24 is less, right? Because it's further down the hole. It's always so weird to think about the 24s and the 18s. Remember, more negative means you're further in the hole, you're less. So the inequality that started as a less than, flip to a greater than. So that's the rule. If you multiply or divide by negative, you flip the inequality. Okay, now we got the rule underway. Now we can actually solve some inequalities. So first off with our kind of our just basic kind of inequality. So we're trying to solve this. We're going to get x by itself. Just like if I was solving an equation, the way to solve these is to get x by itself. So to do that, I'm going to get rid of the 7, get rid of this 2. When you're undoing equations, you always think about doing things backwards. So I'm going to subtract the 7 first, because I want to get rid of this 7 before I try and get rid of multiplication. So I'm going to get rid of that 7. So it cancels here. So 15 minus 7 gives me 8. So 8 less than negative 2x. And again, remember, when you subtract, you never flip the inequality. It's only when you multiply or divide by negative. So the next step, when I want to undo this multiplication and divide by the same number, so divide by negative 2, this is where I'm going to flip the inequality, because now I'm dividing by a negative to undo that multiplication, right? I have to do the exact same thing, same negative, multiplied and divided, cancels. So then I flip the inequality. So I flip the inequality because I multiplied or divided by a negative. In algebra, we'll probably see a lot more dividing by a negative, because usually divide to solve, that's pretty typical. So when you divide by a negative, you know you want to get that inequality and flip it. Okay, so this just becomes x because the 2's are canceled. Over here, I get 8 divided by 2 is 4, and then we get a negative because positive divided by negative is a negative. So my set numbers follow this rule. Now, if you're doing set builder, you could actually just put a frame around this and call it good. That'd be set builder, right? You just put the little squiggly x bar squiggly. But typically, I'm going to ask you to answer these questions in interval notation. It's the most commonly used one. It's a good one to use. So that's what we do here. So we take this set and we write it as an interval. So I think about what this means. It means that my numbers, x stands for my numbers, if you think about it that way, are going to be less than negative 4. Negative 4 is the biggest possible. It's the alligator eating negative 4. The alligator's hungry. It's going for the big number. Negative 4 is the biggest it can get. So the x is going to be smaller. So for this one, I would write this as the smallest possible thing is negative infinity, because you can go as small as you want, right? The numbers, anything smaller than negative 4 works, and then it goes till I hit negative 4. And negative 4 is the biggest possible because that's what the alligator's eating. There's no equals here, so I'm going to use parentheses, right? Parentheses means that you can't include the number. And of course, infinity, we always use parentheses. So this would be our interval notation. So this is interval notation. I want to answer in the interval notation. So that's the answer we're going to be looking for on the test and on the homework. I'm going to be looking for something like this, where it's written in interval notation. If you write the answer and it's just negative 4 greater than x, you haven't finished the question, because I'll put on the test, I'll put use interval notation so that you remember that you need to write it like this. Now this one we do want to graph on the number line, so we're going to go ahead and make a number line real quick and then put a number on here. I'm going to put negative 4 somewhere on here. We have negative 3, 2, 1, 0 would be like here. And we have our interval, our number line, sorry. To graph this, I would want the numbers, again, smaller than negative 4. So the graph of this would look like this. We'd have a circle at negative 4, and we have an arrow that points to the left. I put my arrow above just so it's easy to see, but it's just an arrow going to the left. I'm not going to fill in this circle, because by leaving it open, that tells everybody we don't want to include negative 4. So anytime you have parentheses or no equal sign, like this, you're going to leave it as an open circle. I have seen my math lab and some other textbooks and stuff write the same graph like this, but instead of using a circle, they use a parentheses, because then it matches the interval notation parentheses. So you might see it like this on homework or on the textbook or something. It means the same thing as the open circle. Those are just two different ways to graph the same line, set of numbers, everything less than negative 4. So that would be the graph of that. Okay, let's try another one. Here I'm going to throw in with the fractions at you, because they'll probably do that in the homework and stuff. And we kind of already talked about how to deal with fractions. And thankfully, the tools we used before with equations still work. We can get rid of fractions here, again, just by multiplying by a big enough number. And the number we always want to multiply by is the LCD, the common denominator, because if you multiply by the LCD, you'll get rid of all the fractions. 2, 5, and 10, they all go into 10, right? 2 goes into 10, 10 goes into itself, of course. 5 goes into 10, so 10 is your LCD. So we're going to actually multiply everything here times 10, because doing that will just get rid of all the fractions. It's always nice to just make the fractions go away and make it a problem with no fractions. I don't know about you, but I know most of my math students prefer not to have fractions. So I'm going to take this, I'm going to multiply 10 to the first part. Again, I'm going to cancel as I multiply, so I'm going to think about the 2 here and the 10, and the fact that 10 is 2 times 5, so I can cancel the 2 part of that and just do the 5. So we do 5 times x. So I get 5x for the first part. The next part, when I multiply 10 times this one, well, there's an entire 10 on the bottom here. So that 10 is going to cancel all of that 10, and we're just going to end up with minus 1. So the 10's canceled. Next part, I'm going to do 10 times the next part here. So don't forget you're greater than or equals to. Make sure you keep your inequality there. 10 times this part. Now the 5 part is on bottom to cancel. So the 5s are going to cancel. And we're just going to left the x times the 2 because the 5 cancels. We get 2 times x. And the last part, don't forget, when you're doing this trick, a lot of people forget to multiply the whole numbers. Even the whole numbers get multiplied. And here, there's nothing to cancel, so you multiply by the entire 10. So we get 10 times 2, and you get 20. Okay, that's our trick, just to make the fractions go away. Now we don't have to worry about fractions anymore. We can just solve this inequality. Since I multiplied by a positive, again, I do not change the inequality. I only change it if I divide or multiply by a negative. On the next step, I would want to get x's on the same side. It doesn't matter which way you can do it. You can subtract 5x across, you subtract 2x across. If you're clever, you subtract the 2x across because you go, that way when I'm done subtracting, I'll get a positive number, right? 5 minus 2 is a positive, but 2 minus 5 is a negative. Sometimes you can kind of avoid negatives and you don't have to worry about doing as much of the inequality flipping. So I'm going to go ahead and do that. I'm going to subtract 2x from both sides because that's a good way for me to avoid having to flip my inequality here. 5x minus 2x gives me 3x. This 1 is greater than or equal to 20. Then I'm going to add 1 to both sides. So I'm going to add 1. So I get 3x is greater than or equal to 21. Next step, I'm going to take both sides, I'm going to divide them by 3. So I'm going to divide both sides by 3. So cancel this thing. I'm left with x is greater than or equal to 7. So I divided both sides by 3. Again, I'm dividing by a positive, so I don't flip the inequality. That's why I just get x greater than or equal to 7. Now, again, I want to answer this in interval notation. I don't want to leave it in this as a rule like this. I want to make sure I have a set of numbers. So again, I need to write interval notation. To do interval notation, you think about the smallest possible number and the biggest possible number. Well, now you'll notice the alligator is eating the x, which means the 7 is on the low end. It's the small thing. The alligator would rather eat something bigger. So the 7 is the smallest possible. So I go with 7 on the low end. And then the biggest possible number, well, it's anything bigger than 7, so that's going to go to infinity. Always for infinity, it's always parentheses. You can't include infinity. We never reach it. Now the 7, because I have an equals here, does get included. So the 7, I use a bracket. And that would be my interval notation for this one. So it's everything from 7 to infinity, including 7. Okay, I want to graph this one, so if I put like 0 here, I have 1, 2, 3, 4, 5, 6, 7 would be here. 7, and you could put more values in there, but 7 is enough for me because I can put my circle at 7, fill it in because it's an equal to, right? It's a bracket, so we want to include 7, and then I want numbers that are bigger than 7, right? Things are bigger than 7, so I'm going to go to the right here. Everything bigger than 7. Again, you can see this inequality here, right? Inequalities, the alligator's eating the x, so my numbers need to be things bigger than 7 because 7's on the small end. It's the small value. So that's how I do that. And again, if you want to do this with parentheses or brackets, you would just do a bracket. So we do brackets, whether it's equals to or a bracket. And it means the same thing as if you do a circle. I have no preference. So if you're doing a test question, you can answer either one of these. I don't care which. I just want to show this because that's my math lab. This is actually how I learned it back in the day. So I'm fine with both. So that's what your answer is. Okay. Now that was solving inequalities. I've got a couple more examples of this, and then we're going to talk about something else too. So let's go ahead and do a couple more examples. This one, only the big difference here is now I have parentheses. So you can see I've got parentheses on both sides. Just like equations, when we have parentheses in an equation or an inequality, we like to get rid of them. They just don't make things easy. They make things complicated. You can't really work with the stuff inside until you get rid of the parentheses. So the trick is to distribute. Remember that whenever you have a parentheses, you distribute. It just means whatever's being multiplied times that parentheses, you multiply it to both parts, and then you can get rid of the parentheses. So I can do 2x times 3x, and I get 6x squared. I get 2x times 1, so I get minus 2x minus 7, greater than, over here I get 3x times 4, I get 12x. I get 3x times 2x, I get plus 6x squared. Again, when you multiply x times x, you get x squared. Now I saw this one and I actually stole it from the homework because I saw it and I went, that's so mean. How come we're making students solve problems with x squareds in them before we've actually talked about doing that? This is in your textbook, and I was kind of pissed with your textbook. And then I noticed something when I went to start solving it. I realized that when you do this, the first step you're going to do is you're going to try and get all the x squareds on the same side. Well, since the x squareds are the same thing, when you subtract one of them away from the other one side, and you have to do the same thing to the other side, They cancel, right? Those guys cancel, so they just go away. So even though it looks like it's going to be a weird, hard problem with these x squareds, all your homework questions will do this. So if you see an x squared, don't freak out too much. I know it looks scary and looks hard, but actually, you get rid of the x squared part, because when you go ahead and you subtract it from both sides like this, or add whatever you have to do to cancel it, it gets rid of it, and you're just left with what's left. So here I'm left with the minus 2x minus 7 and the 12x. So it looked way worse than it was. You know, it looked, oh man, x squared, but they just go away. It's not that big a deal. Okay, let's finish this off. I want to get the x's on the same side. Again, we like to get them positive. So if we're going to move the 2x over, I'm going to get positive because I'm going to add 2x to both sides. So that's what I'm going to do. I'm going to add 2x to both sides. That way I can get rid of this minus 2x. So we got minus 7 is greater than, what is that, 14x? 12 plus 2 is 14. Last step, I'm going to undo this multiplication. I'm going to divide both sides by 14. That way I can get rid of this 14 on this side. And 7 divided by 14, it doesn't divide nicely, but it does simplify. Make sure you always simplify your fractions. Now, if you're one of those students who are like, I hate simplifying fractions, they're a pain in the butt, it's hard to do, or I mess it up all the time, your calculator I told you to buy for this course, it will simplify fractions. You can just type in something like that, 7 over 14, 7 divided by 14, right as a division like that, so it looks like a fraction. Hit enter, it gives you a decimal. But if you hit the math button, so the math button's right down here, it says math, underneath these top two buttons is math. The very first option is to turn it into a fraction option. So I hit enter twice, and it will turn it back into a fraction. It's always a simplified fraction. So this is a cool thing, your calculator will do this. You can always simplify any fraction you give it. Just type it in as a fraction, a division, and then when it gives you a decimal, just turn it back into a fraction, and it will simplify it for you. So if you want, you can just make the calculator simplify that and see that this is actually x is less than negative 1/2, right? It stays negative. I just simplify the 7/14 to 1/2. Now again, don't forget about interval notation. On the test, if you write your answer like this, I'm going to count it wrong because you're missing the interval notation. Now you get most of the points for solving, but you're going to lose a couple of points if you don't write an interval notation. So interval notation, again, you need to know this notation. That's why I'm being kind of hard with it, being a stickler about it, because I want you to use this the whole semester long. So we're introducing it now, very much so. So here I'm going to take this, I'm going to write my set of numbers. Again, I'm thinking about the smallest possible and then the biggest possible. Always start with small and then go big. I want numbers less than negative 1/2. So this needs to be smaller. So it means I can go as small as I want as long as it's smaller than negative 1/2. So negative 1/2. That's the biggest I can get, right? The alligator is eating the negative 1/2. It's on the big side. There's no equals, so use a parentheses, and infinity always has a parentheses. And that's the answer set. That's the set of numbers that make this true. This is the set of numbers that work. They're the values that make this inequality true. Okay, 2 more to solve. These ones are kind of weird ones, so I wanted to show them to you. So notice this one, I've got 2x plus 1 less than 2x minus 5. So again, I want to get all the x's on the same side. So I'm going to subtract 2x from both sides, trying to get all the x's on the same side. And when you do that, you'll see that, of course, both of the x's cancel, and we're just left with 1 is less than negative 5. Now we saw this before with equations, right? We saw sometimes it work and the x's disappear, and then we knew it was either no solution or all real number solution, and it's the same thing here. If your x's all cancel and you're just left with an inequality, you just decide, is it true or false? And it tells you what's going on. Well, 1 is not less than negative 5, right? Because negative 5 is a negative. This is smaller, so this is false. And that means that no matter what you put in here, no matter what you put in for x, this won't be true. So that means there are no solutions. Now, if I want to write this in interval notation, most people, when they use interval notation, they want to write nothing, no solutions. They use this circle with a line through it. It's called the empty set. That's just a fancy name for it. The empty set, it's the set of no numbers, nothing's in there, nothing works. So there are no values where 1 is less than negative 5. That doesn't work for any values. No matter what you put in for x, you can't make 1 smaller than negative 5. It doesn't work. So if it's false, it's no solutions. We'll use the empty set. We're doing interval notation. Let's try one more. This one, a similar thing happens, right? I subtract 3x from both sides on this one. So trying to get rid of parts. I subtract 3x from both sides. And again, you see that the 3x's cancel on both sides. We're left with negative 2 is greater than or equal to negative 4. So the x's cancel. We're just left with this inequality. If I look at it, I say, okay, is this true? Is negative 2 bigger than negative 4? And yes, it is, right? Because remember, the negative 4 is smaller because it's more in the whole. So this one's actually true. This one's true. Negative 2 is bigger than negative 4. So this one, x doesn't matter because no matter what, negative 2 is bigger than negative 4. And this is the situation where anything you put in, this is going to work. So this is going to be all real numbers. So again, the trick is, if the inequality is always true, then it's all real numbers because it's always true. If you stop and think about what happened in these problems, you'll notice the first one, we had 2x plus 1 and 2x minus 5. Well, if I add 1 to a number versus subtracting 5, then this side's going to have to be bigger, right? Because I went up versus this side where I went down. And that's why the inequality doesn't work. That's why it's false. Because here it says that this side's smaller. But no, this side has to be bigger. Kind of same thing down here. If I subtract 2 or I subtract 4, well, this side should be smaller and that side should be bigger. And that's true. They said that this side is smaller than that side. And so it's always true. So you can see why these kind of both end up working the way they did. So again, this one's true always, so all real numbers work. You can plug anything you want in for x. Now if I want to write that in interval notation, so if I want to do interval notation for this one, all real numbers, another way to write that in the interval notation is just from negative infinity to infinity. That's all real numbers, right? Because everything fits. If you go from negative infinity to infinity, all the way from left to right, everything, that's all real numbers, that's everything. So this is everything, that's nothing. The difference. Empty set, circle line through it, it's nothing. Negative infinity, that's everything. Okay, one last part to this section. Last thing I want to talk about is what we call compound inequalities. So a compound inequality is an inequality that's going to use the word and or the word or to join two inequalities. So two inequalities are joined by these words. So these would be examples here. So I have this one right here. So this inequality, negative 3 is less than 5x and 5x is less than 12. Or you combine them with an or. Say 2x minus 3 is less than 9, or 2x minus 3 is greater than 21. So the or combines them. Now you can combine and inequalities by writing them like this. So this is actually an and inequality. They don't say the word and here, but if you see something like this, this is actually the same as saying negative 14 is less than x minus 7, and x minus 7 is less than 14. So this is a compound inequality. This is one where we take these two expressions, and because they have the x minus 7 in the middle in both of them, we can combine that together just to have one x minus 7, and then just write the whole pair of inequalities as one 3-part inequality. So if you look at this, you can kind of cover up one side, and you can see the first inequality, negative 14 is less than x minus 7. Cover up the other side, you see the other inequality, right? X minus 7 is less than 14. These do happen a lot in our class, so we'll see these. So I'm going to work with a few of these so you can kind of get used to them. But the idea here is it's just taking a compound inequality and kind of rewriting it as a compound, as like one thing, instead of having to write it as separate things. Okay, let's solve. So now you got to be really careful whether you're solving an and inequality or an or inequality, because and means, for math, and means that both must be true. So in math, we'd never say that a number is odd and even, because it can't be both, right? You're either odd or even. You can't be both. A number could be bigger than 7 and even. 8 is bigger than 7 and even, so they could be both. Or means that either one could be true. So either can be true. And it's okay for both to be true as well. Or is really not picky. It doesn't care if the left is true, the right is true, or both are true. So either can be true. So if I say a number is bigger than 7 or even, well then 9 would work, right? Because 9 is bigger than 7. It's not even, but that's okay. We just need to be one or the other. So or is not picky. It says either one needs to be true. So when I see an and inequality, that means that my answer has to make both inequalities true. It has to be a number that this is true and this is true using that number. And to do this, if it's separate like this, I'm just going to solve each inequality separately and then look at the two answers and find out where they meet up. What numbers answer both sets. So for this example, I'm going to solve this first inequality. Again, I want to get x by itself, so I'm going to subtract 3 from both sides. Negative 8 minus 3 is negative 11. Bring the 2x down. And then we cancel the 3, right? That's why we subtracted 3 to get rid of that 3. Next, I'm going to divide by 2 on both sides. So divide by 2 on both sides. Get rid of this 2. And you see that our numbers have to be bigger than negative 11 halves. So if I was going to write this as an interval, I'm just going to write this interval. This interval would be all the numbers bigger than negative 11 halves. So I'd start with negative 11 halves and say go off to infinity. Any numbers bigger than negative 11 halves would be this set. So it's got to be part of this set. Now if I do the next one, let me do this in green just so you can see the difference. So this set, I'm going to again subtract 3 from both sides because I have this 3 here that I want to get rid of. I can get that 2x by itself. 7 minus 3 is 4. I can divide by 2 on both sides. Get rid of this thing. So x is going to be less than 2. So there's going to be a set of numbers that are smaller than 2. So this interval would be numbers from 2 down to negative infinity. And that would be set. Again, there's no equals on either of these. That's why I'm using parentheses for the numbers. So my answer to this is going to be both this and this. So it's going to be an and. So it's going to be the numbers that are in this set and in this set. So if you think about this, if I made a little number line real quick and looked at this, you would see that the blue line, this line here, would be over here at negative 11 halves, and it would be a line that goes from there to infinity that way, right? That's what it would look like there. The green part is going to have a value over here, say at like 2, and it's going to have a line that starts at 2 and goes forever that way, right? Like that. Now, and means it has to be both, so and set is going to be this region right there. That's going to be your and part. It's the part that is both. That's what and is. And has to be both. Can't be one or the other. It has to be both because it's and. So the answer to this problem, the solution set for this problem, is going to be numbers between negative 11 halves and 2. So the answer is going to be from negative 11 halves to 2. That's the answer because it's in both sets. So it's both in this set and in that set. So if I pick a number in here like 1, right? 1 is between these two numbers. 1 is bigger than 11 halves, negative 11 halves, and smaller than 2. So 1 fits in this set. If I try 5, 5 is bigger than negative 11 halves, but it's not smaller than 2. So 5 is not part of this answer. So numbers like 5, 6, 7, these don't work. Numbers smaller than negative 11 halves, things like negative 10, negative 20, they don't work. Only the numbers in the middle range work. So when we're doing and like this, got to put the compound inequalities, we have to put them together. So if you have two inequalities, you solve them both, and then you look at those two sets and then mesh them together. And it has to be in both sets. It's the overlap. Where do they overlap? That's your and. And is the overlap. Okay, let's try one more. This one is an or now. So instead of an and, it's an or. So let's solve this one. Again, we'll solve each part separately. So we're going to solve the first part. Here I'm going to add 3 to both sides. So I can get rid of this thing. So we get 3 plus 3 is 6. Less than or equal to 14x. We divide by 14 on both sides, right? So divide by 14. Cancel this guy. 6 divided by 14, it doesn't come out nicely. You can't divide 6 by 14, but it does simplify. Both these divide by 2, you end up with 3/7. So again, if you don't like that, you can put it in your calculator to double check. So this would be a set of numbers for this one. And if I wrote this as inequality, I'm looking at 3/7 is smaller. Alligators eating x is bigger, so I'm going to say 3/7 to infinity. Parentheses is for infinity because infinity is always parentheses. But since there's an equals line here, the 3/7 is going to get a bracket for including the 3/7. Okay, let's try the other one. If I do the green one here, I'm going to add 8 to both sides. So I can cancel this minus 8 here. So we get x is less than, what, 20? I got my inequality done, so now I can divide by set. My answer to this is just numbers bigger than 20, right? Smaller than 20, because x is less than 20. So this is the biggest possible number I get. So I'm going to go from negative infinity to 20. Parentheses, because I can't include 20. Parentheses, because you can't ever include infinity. And then or means that you could be in either set. So you can either be in the numbers that are bigger than 3/7, or you can be in the numbers that are smaller than 20. And either one works. So now if I write this in a number line, you can see how a number line kind of helps you visualize what's happening here. You see a number line here. You mark off, you got like 3/7 is down here, and 20 is here. You'd see that the 3/7 piece, it's going to be from here going forever that way. The 20, this 20 piece, it's going to be from negative to 20, it's going to go like this, that way. Now, you may be thinking, oh, it's the middle piece. But no, this one says or, not and. So it doesn't have to be both. It has to be either. So you could either be in the green line or you can be in the blue line. So numbers like 22 up here, they work because 22 is bigger than 3/7. Numbers like negative 10 down here, it's less than 20, it works. So this one's actually everything. This one's all. And it's because of the or word. Now I'm fine with either arrow. So the answer for this one is actually going to be from negative infinity to infinity. Because everything works. Because this piece has everything going up, this piece has everything going down, and there's no gap in the middle. Now you could make one of these where you end up with a little bit of space in the middle, and you might have two pieces, and that can happen. But in this case, we just end up with one big piece. So that's what our answer looks like. It's one big set, everything works, everything fits. You either solve that set or you solve that set. You don't have to do both, you just have to one or the other because of the word or. Okay, two more examples of this and we're done with this section. It's all about solving these inequalities. Okay, so here you notice this is one of those compound inequalities. So again, this is the same thing as writing that negative 6 is less than 1/3 4x plus 2. And, because these compound inequalities like this is a and compound inequality, so you can write the first one and the second one, that 1/3 4x, oops, forgot my 4x plus 2 is less than 4. So both of those have to be true. If you prefer to solve them separately, you can write it like this, and you can solve it separately, and that's totally fine. Me, this gets kind of lengthy, time-consuming. I don't really like to rewrite it, so I am going to just solve it as it is. But when I solve this, I got to be careful, because now since I've got 3 parts here, instead of just working on both sides, I have to work on all 3 sides at the same time. So I'm going to show you how this works. I'm going to take this one, I'm going to solve it. First thing, I don't like having fractions, so I'm going to use the trick that we've always done and just multiply by the LCD. In this case, the LCD is 3. So I'm going to multiply everything here by 3. And that will get rid of this 1/3 for me. So I'm going to take times 3, I'm going to do 3 times 6, I get 18, so I get negative 18. When I do my 3 times my 1/3 here, the 3 and the 1/3 cancel, because if you do take 3 times 1/3, 3 and 1/3 gives you 3/3, which is just a 1, and multiplying by 1 just makes things go away. Another way to think about this, you can think of this as dividing by 3 and multiplying by 3, and they just cancel. So I'm actually just going to let those cancel. I'm just going to leave the 4x plus 2. And since there's no number in front anymore, because the 3 cancels with the 1/3, we don't need the parentheses. So I'm writing just 4x plus 2. And then the last part, I'm going to multiply that 3 times this 4 over here, and I get 12 on this side. Okay. Now I'm going to do the next step. I want to get this x by itself, so I'm going to subtract 2 from both sides. Subtract 2 from both sides here. Cancels this 2. So we got 4x here. 12 minus 2 gives me 10. Negative 18 minus 2 gives me negative 20. Okay, and then now I want to get rid of this x, this 4 in front of this x, so I'm going to divide by 4. But again, I'm going to do it to all 3 parts. I'm going to divide this by 4, divide this by 4. So when you're working with a compound inequality where it's 3 parts, you're working on all 3 parts at the same time. Again, you could think of this as 2 things. I'm going to, solving this side where I divide both sides by 4, and solving this side where I divide both sides by 4. That's why it's okay to do 3 parts, because again, I'm kind of doing 2 different things at the same time. I'm just combining it all into one step, one process. Okay, divide by 4 here, cancel the 4's, you get x. 10 doesn't divide by 4, it doesn't come out nicely, but you can simplify. These both divide by 2, so you end up with 5 halves. 20 does divide by 4, that gives us 5. And a negative divided by positive is a negative. And then we have our common inequality. Now the nice thing about solving this way is when you solve this way, when you're done, you actually already have your interval notation. Because all you have to do is look at the smallest number and the biggest number and write those down. So negative 5 is the smallest, 5 halves is the biggest. Because there's no equals here, there's just straight inequalities. We're going to use parentheses, and that's our answer. So that's why I kind of like doing it that way. When I'm done, I've got my answer. I don't have to like rewrite and figure out how it looks, because you'll have your smallest and your biggest just there for you when you're done. And again, that's because this is an and inequality. So it's the numbers between those 2 values. Okay, let's do one more. This is another or, so we're going to do each one, and then we're going to get those 2 sets and combine them. So let's solve this one. So I got, first off, 3x is less than 24 minus 5x. I want all the x's on the same side, so I'm going to go ahead and add 5x across. Add 5x. So they cancel this side. 3x plus 5x is 8x, less than 24. I'm going to divide by 8, because that will undo that multiplication here. So I can cancel that 8. So I get x is less than 3. With this, because I'm doing or, I'm doing 2 separate pieces, I'm going to go ahead and write this interval notation. So I'm thinking that number is smaller than 3. It's going to be from negative infinity to 3. Again, alligators eating 3, it's the biggest thing. Parentheses, parentheses, infinity is always parentheses. There's no equal sign, so it's parentheses. This one over here, I'm going to subtract 6 from both sides first. So get rid of that plus 6. 3x is greater than 21 minus 6 is 15. So 15. Divide by 3. So I'll undo that multiplication. So I'm going to get rid of this multiplication by dividing by 3. See that x is, oops, don't flip it. No reason to flip it. Divide by a positive number. X is greater than 5. It should be x greater than 5. And then that one, again, I'm going to write that as an interval notation. So interval, I want the numbers bigger than 5, right? Because alligator's eating the x. So 5 is the smallest. So this is going to go 5, 5 to infinity. Again, there's no equals here, so parentheses. You always got to watch for those equals because those brackets will get you on the test and the homework and stuff. Okay, last thing. So this one's 2 sets. And you notice if I graph these two, if I have my 3 down here and my 5 up here, and I make my piece from my 5 that goes this way, and make my piece from my 3 that goes this way, you'll notice they don't overlap, right? There's no overlap. Before we had overlap and we said everything works because or you just put it all together. This one, there's no overlap. So this 2 pieces are actually separate. So my answer for this is actually both pieces. I need this piece and this piece because or says this could work or that could work. Small numbers like 1, well, 1 makes this one true, because if you put in there 1 is less than 3, it works. And big numbers like 7, well, that works because 7 is bigger than 5. 7 makes this one work. So all those numbers have to be counted. So the way I do that is I just take both intervals, these 2 separate intervals, and I put a big union symbol between them. So we use the union symbol. It looks like a U, it just doesn't have a tail. In my math lab, when you're working in my math lab, there is a button for this union symbol. So you use that union symbol button, and that's how you get it in there. But so your answer is actually this whole thing. That would be your answer for this one, because both pieces need to be included. And then the union just puts it all together to make one big thing out of it. And this is everything except for the numbers between 3 and 5. Doesn't include 5, doesn't include 3, and the numbers between those don't work. But anything smaller than 3 works, anything bigger than 5 works. Okay, so that's solving inequalities. You should be ready for solving these compound inequalities. We will see these come up later in the semester for different reasons. So these will come back, these compound inequalities, so it's good we've introduced them now. But you should be ready to solve compound inequalities, whether they're and inequalities or inequalities. You should be ready to solve just regular inequalities, sometimes with weird solutions like no solutions or infinitely many all real numbers. And you should be ready for things like having to flip the inequality when you divide by a negative. And then you should be ready to use these notations, the roster method, intervals notation, and that set building notation. And that's outcome 6. Hope you have a good time doing this homework. It goes well for you. As always, if you have questions, use that Ask My Instructor button. It's the best way to ask me questions. Because if you just send me an email, I might not know what class you're talking about. I always have lots more than one class I'm teaching at a time. So use the Ask My Instructor button. It's a great way to help me know which class you're asking about, and then I can usually respond a little bit faster. So make sure you're using that. It's a great way to ask questions, even if they're not questions about the homework. You can ask other questions about the class and use the Ask My Instructor button in the My Lab, because that will let me know which class you're talking about, what homework set maybe you're working on, that kind of stuff. It's really nice. So, all right, I'll see you on the next set.